Hello everyone, I am Irene A from the class O2 of the Astronautics subject. So for this assignment, I chose the Mars Atmosphere and Volatile Evolution Mission, or commonly shortened as MAVEN, to be reconstructed. So first, we are going to get know, have a little bit of knowledge of the MAVEN itself in general. So, MAVEN, or the Mars Atmosphere and Volatile Evolution, was selected as one of a part of NASA's now-cancelled Mars Scout program in order to explore the atmosphere and ionosphere of the planet and how they interact with the sun and solar wind. So, the mission is, of course, will study about the ionosphere and atmosphere of Mars and characterizing their current states, as well as determining the rates of loss of gas to the space today. And this measurement will allow researchers to extrapolate backward in time to determine the total loss throughout the planet's history. And this is the interesting part. So, TLDR, we are going to know about more about the Mars and how whether it could sustain our life as humankind or not. And MAVEN is one of the spacecraft launched in order to obtain this information. And now we are going to get to know more about MAVEN as a spacecraft itself, more technical things. So it is manufactured by the Lockheed Martin Space Systems, and it has a launch mass of 2,454 kilograms, or around 2 tons. And it was launched at November 18, 2013 at 28 minutes past 6 p.m. UTC. And it is launched at CCAFS Space Launch Complex 41 at Florida. And it has a coordinate of 28.5839 degree to the north and 80.5828 degree to the west. And it safely landed at September 21st, 2014 at 24 minutes past 3 a.m. UTC. So it took 307 days for MAVEN to reach its destination, and it is powered by Atlas V401. Its tail is AV038, and the propellant is hydrazine or dinitrogen tetrahydrate. And the propeller mass is 645 kilogram. It has a characteristic energy when it's launched of 12.2 kilometers square per second square, and it has length of 11.43 meter from its wingtip to the other wingtip, and it has width of 2.29 meter. Its height is 3.47 meter, and its high gain antenna is 2 meter. And the contractor of this MAVEN is United Launch Alliance, and it is now still operating. Although the initial mission, the mandatory mission, was already finished around 2 years, 2 years after its launch. So now, since we are going to reconstruct it, how would the data be? And will it be different, or will it be the same, or will we see any anomalies? Let's find out. So first thing, in order to reconstruct the mission, we should find the basic variables, such as the perimeter of the Earth, perimeter of the Sun, etc. It's the basic thing. And we have to make some assumptions. Why? Because we are going to calculate by hand manually, and I assume a few things in order to make the calculations easier. So for this, I have 4 assumptions. I assume 4 things. The first one is its orbit is circular, so the altitude is always the same everywhere, and the inclination angle is 0 degree, and the taken altitude from Earth's atmosphere is 150 kilometer. It is taken from the real data, and I took the shortest distance, and no other spacecraft or space items, or as well as natural phenomenon impact considered in my calculations. Moving on to the basic known variables. So we have new E, new M, new S, respectively. EMS are Earth, Mars, and the spacecraft. We have the perimeter of the Earth, Mars, the distance between the spacecraft and the Earth, and then the Mars and the spacecraft, and of course the ISP of the hydrogen for the propellant calculations later. So second part, we're going to calculate things in here. In the parking orbit, the main focus is to calculate the velocity of the spacecraft to the Earth. And I put here the known variables that we've stated before in case we forgot where should we input, and I try to highlight the used variables in here in orange. So the spacecraft velocity to the Earth, denoted by VCE. It has a formula of square root of nu e over RE plus h. And as we see, we have it here, we have it here, and we have it here as assumed. So we can easily obtain the value of the velocity of the spacecraft to the Earth is 7.82 kilometers per second. Easy. And then next, we're moving to the third part. Third section is the hyperbolic escape trajectory. It is a quite long section because first Mars is quite far and it took a lot of calculations. It's not the same as how we calculate it, not interplanetary. So we have a lot of things to calculate, to consider. And the things that we are going to calculate is the Earth to Sun velocity, hyperbolic escape velocity, pericenter velocity, and change of velocity. And we should note that aside from these four things that we are going to find, we of course have a lot more calculations to go, because some of them cannot be directly obtained. We have to obtain some other variables first. Let's find out. So first is the velocity of Earth to the Sun. If you notice, it's quite similar with the earlier formulations. It was a square root of nu s over res, and we have it here, one of them. And we can easily obtain the velocity of Earth to the Sun of 29.78 kilometers per second. And then we have to calculate the semi-major axis, or A, of the heliocentric orbit. It is denoted by A, and the formulation is RSE, we have it here, plus RSM, we have it here, divided by 2. And we can obtain A equal to 188.75 times 10 to the power of 6 kilometer. That was a lot, of course. And then next, we can calculate the pericenter heliocentric velocity, as what I mentioned at the opening of the section 3. We cannot always calculate every main variables directly. Just like this, we have to calculate the semi-major axis first. So the pericenter heliocentric velocity, denoted by VPH, is square root of nu s in here, times 2 over RSE in here, minus 1 over A. We obtained it earlier, and we compute the values, and we can easily get VPH equals to 32.733 kilometers per second. Moving on to the hyperbolic escape velocity, or we can also calculate the C3 in here by square rooting it later. So V infinite, it's denoted by V infinite, equals to VPH mean VES. We've obtained it in the slide before this, and we also obtained the Earth to Sun velocity. We can just subtract it, and we can get the hyperbolic escape velocity is 2.95 kilometers per second. And if we square root it, we can get C3. We are going to meet this equation again, and maybe some of the previous equation again in the next section as well. So we are going to calculate the eccentricity, one of the main thing that we should calculate, although despite it's not listed at the opening section. But first we should calculate the AH. AH is easily just nu e. We have nu e in here divided by the escape velocity that we've obtained earlier, and we get the AH is minus 45,816 kilometers in minus, and no need to worry. Why? Let's find out. Because the eccentricity is 1 minus RPH over AH. AH is here. RPH, RPH is consists of RE 6,371 plus the assumed assume altitude. So we can get the eccentricity of 1.1423. So moving on to the pericenter velocity of hyperbolic trajectory, or denoted as VP. VP equals to V infinite, or the escape velocity, times the square root of eccentricity we obtained it earlier, plus 1, and divided by E minus 1. And we just compute it here, easy. We can get the VP 11.40 kilometers per second. So change of velocity. Change of velocity is, we can basically just subtract the earlier obtained in here pericenter velocity of hyperbolic trajectory and the VES, the Earth to Sun, and we can get the delta V is 3.6 kilometers per second. And then moving on to the heliocentric trajectory. And in the heliocentric trajectory, we are going to talk about time, the orbit transfer total time in the final product. And we are using the third Kepler law in order to calculate the orbit transfer denoted by P, and it is 2 pi times square root of semi-major axis to the power of 3 divided by nu s. And we can get it in second. We convert it to days, and we get 517.7 days. And then the T is P over 2. P is 517.7 days plus 15. And why 15? Because for Mars and Earth, the launching period of the rocket to the parking orbit needs 15 days in Earth scale. Thus, the total time needed for the spacecraft to reach Mars from Earth should be added by 15. And then moving on to the arrival hyperbolic trajectory. So for the arrival hyperbolic trajectory, we are going to meet C3, the characteristic energy again, and the V capture, or maybe precisely the delta V capture. So first, we are going to calculate C3, and it could not be obtained directly. First, we should calculate VMS. We have square root nu s, we have it. RMS, we have it. We got it. It's always stated in here. So VAH as well, we have the value of the nu s. It is, sorry, the formula is square root nu s times 2 over RSM minus 1 over the semi-major axis. We've made this before. It's just different value because it's now in Mars. So we got it 15,000.87 kilometers per second, and we can calculate the V infinite, or the or later B square root SC3 just by subtracting this and this. We got 5.98, and by squaring it up, we got the C3, and the C3 has a value of 35.76 kilometers square per second square. Moving on to the spacecraft's orbit velocity around Mars, or denoted as VCM, we have square root of nu m over rm plus h. Again, we've met this before, just in different value. So we just compute, we have nu m, we have rm, we have the assume h, and we can obtain the spacecraft orbit velocity around Mars is 3.48 kilometers per second. So moving on, again, we met semi-major axis and eccentricity again. So we are familiar, of course, with this. And A is equals to nu m over V infinite to the power of 2. We can compute it. We have nu m, we have V infinite, the earlier, the 5.98. And we get it in minus again, minus 7,160.64 kilometers. Again, no need to worry. We are going to calculate eccentricity, it's fine. So we calculate we input the A in here, the RCM, we have it in here. And we add it with the h over the semi-major axis again. So we can get the eccentricity of 0.51. And then next, it's actually different section, but I plug it into one because it's quite short in calculation. So first is the VP, or velocity of pericenter hyperbolic before capture. It's quite similar because we have the variables all in here. And then we can get the VP of 7.68 kilometers per second. And how to calculate delta V capture, of change of capture velocity? We can just easily subtracting VP NVCM, the spacecraft and the Mars earlier. So we can get the delta V capture is 4.2 km per second. And why we should calculate the delta V capture? Because we are going to use it in the propellant calculation. It has the relation. So for the section 6 of propellant, we are going to calculate the propellant's mass, the hydrogen's mass. So for propellant mass, it has a relation with the previously obtained change of capture velocity. It is equal to ISP. We have it here. Finally, it use times gravity, local gravity times ln of uh, the vehicle's mass over the MO is launching vehicle mass, and the MF is going to be our propellant mass. So by converting delta V, it is previously in kilometer per second to meter per second because I adjust it to match G and meter per second. So we can get the the MO over MF after mathematically calculating this of 3.93, and we get the MF of 624.428 kilogram. So if you notice, maybe, do you notice something different? Because the numbers that I mentioned before in the Get to Know MAVEN is actually something is different. So to make it clear, let's just compare the real and calculated data. For this, I'm taking 3 variables. First is time, second is the energy, and the third is propellant mass. So for the real one, we can always go back to the earlier slide. So the real time MAVEN used to safely land to the destination is 307 days, while calculated is only 274 days. The 13 and C3 is 12.2, the calculated is 35.76, quite massive difference. And for the propellant mass, it is actually 645 kilogram of hydrogen, but we calculated is only 624.428 kilograms. So we can obtain the error percentage. For the time, it's 10.74%. For the energy, is 34.11%. And for the propellant mass, is 3.18%. So why are this happening? We are calculating the same spacecraft as MAVEN, in the same space as in the Milky Way, but why is it different? Again, we should recall to the beginning before our number saga, number fiesta. So I said that I assume things, and that is actually one of the reason why it is different. So I assume 4 things, this 3 and this 1. I just divide it. So I assume the orbit shape is circular. Well, in fact, the orbit shape is elliptical. So it will affect the altitude. The altitude that I took, because this is the assumption fashion, the altitude that I took is 150 kilometer. All are the same because it's a circle. But in reality, it's actually elliptical. So it is not going to be the same altitude over time. And the inclination as well, I assume it as 0 degree, but it actually has a 7.5 degree of inclination. And also I neglect the other space occupants and natural phenomenon, because it is that there must be a lot of things, and it's quite variables to take into account. That's why I didn't take it to calculation, despite those might affect the spacecraft. Henceforth, those 4 factors must be, I'm quite certain, why we have different data that we calculate by manually earlier together and the data that actually happened. So that's all for me. Thank you for listening to my short presentation of the MAVEN spacecraft. So this has been Irene from Class 02. Thank you, everyone. Goodbye and have a nice day.